Hello, everyone. Today we're going to talk about how you convert a hexagon, right, to a chair conformer. Okay, so before we start with anything, I just wanted you to visualize what a hexagon looks like, right? So this is a hexagon. This is what you will be given in the problem when you're solving the problems, right? And then what we see in this problem is actually that the orange ball, right, in that hexagon is facing towards me, right? So whenever you'll see a hexagon with on the wedge, like we have talked about before, the wedge is the bond which is facing towards me, right? So the orange and the reds are facing towards me, and the green is facing away from me, right? The green is facing away from me. And then the problem is how you go from this structure to a chair conformer, right? And because they're conformers, right, we can just convert from one to another without actually breaking the bond. So let's think about visually how you can just do that, right? If this is your chair conformer, right? Sorry, hexagon, then all you got to do is like move it around such that, right? Move it around such that now this hexagon looks like a chair conformer. We'll talk about it later, why a chair conformer is preferred, or this kind of a conformer is preferred over other conformers, and why this is so stable that every time we write a hexagon, right, we see a hexagon, we want it to, or the molecule itself converts itself, or it likes to sit in a chair conformation because of how stable this kind of a conformation is. All right. Okay, and now what we see is that all the bonds, right, that were facing towards me have now ended up facing up top, right? So the bonds which were coming towards me have ended up facing the top, or you can say they're facing up, all right? And the bonds which are facing away from me, or the bonds that you'll see in your drawing on a plane of paper, if they're facing away from me or if they're on the dash bond, they will end up facing down. So they're facing downwards. Cool. So this is what we need to know. That's what we see in the structure, correct? And now that's what we have to show on a plane of paper. So, well, obviously, if you move the molecule around, it's so easy to know how the bond which was facing towards me ended up facing up, right? The bond which was facing away from me has ended up being at the bottom. So that's what you have to know. This is the previous knowledge that you have to know before you do that work on a plane of paper. So I would recommend anybody trying to play around with the molecules, go ahead and draw out your molecules on a software. The one that I'm using right now here is Avogadro, or you can also use molecular kits. They work the same way. Okay, all right. And now let's do that on a plane of paper, correct? So if I draw out what I exactly had on my 3D, right, to a 2D, you have a plane. You're drawing in a plane, and what we had was facing above me or facing towards me was the red ball, right? And then again, facing towards me here was actually it was orange. Okay, so this was orange ball, and then this was red, and going away from me was a um, chlorine, or actually a green ball, which represents chlorine actually. So I will write down 3 steps in order for you to convert that structure to a chair conformer, right? So to do that, the first step, I would say, draw out your chair. So the first step is draw out the chair. Okay, so when I draw out my chair, okay, so you can draw any 2 ways. We can have our chair drawn out in two ways, right? It can be either this, or it can also be that, but I want I like the first one better, so I'm going to continue writing my structure on the first one. You can choose to pick any that you want to. They both will give you the same results. All right. I'll continue working on the first chair. Okay. And then the second is number. The second is the second step towards converting your hexagon to a chair conformer is number your carbon on your hexagon and on your chair. And this is really important. So you have to keep in mind here that when you're converting from your hexagon to a chair, the numbering has to be the same, meaning that if I say 1, 2, I can choose any atom as my number 1 carbon, right? It doesn't matter. So if I just say 1 here, 2 here, 3 here, and 4 here, 5 and 6. So you have to keep in mind that if you are numbering your atoms clockwise, right? This is a clockwise numbering, then the numbering on your chair also has to be clockwise. Again, it doesn't matter what carbon you choose as carbon 1 on your chair, but you have to remember that whatever carbon you choose as the number 1 carbon has to be, or the second carbon has to be in clockwise direction of your numbering. Meaning that if you choose this as your number 1, right, then this has to be 2, 3, 4. And then if you had chosen anti-clockwise in your hexagon, right, you can still again choose anti-clockwise in your chair as well. It doesn't matter. You just have to be consistent with your numbering in your hexagon and in your chair conformer. Okay. So now let's suppose that that's what I chose as my numbers for my chair conformers. For my chair conformer, that was step 2, just number both the atoms. And then the step 3 is actually use existing knowledge, something that I just showed you using 3D structures. Use existing knowledge to place your substituents. So what does that mean? So like I said previously, that if 1 is facing, this is facing right towards me, because every wedge represent bond facing towards me, right? That will lie towards me. That will, hold on, let me just highlight that really quick. That will lie where? That is going to lie facing up. Okay, so now if I really quickly go from this hexagon, okay, and then I'm going to make sure that atom 1, I'm going to make sure this is orange, atom 1, red, green. I'm going to make sure that atom 1, this is equivalent to this chair conformer. I'm going to make sure that atom 1 is this atom, right? You want to make sure that you're matching the numbers that you already chose in your step 2. And now this is orange, so then this is gonna face up at orange, right? Every atom has 2 kinds of bonds. One is facing up and one is facing down. So this is the bond facing up, and on all of these atoms, these are the bonds facing up. Okay, and this is the bond facing down. This is the bond facing down, right? This is the bond facing down. This is the bond facing down. Okay, and if this is the bond facing up, right, the orange ball would end up on that one. This is the bond facing down, because every chair would have bond facing up, facing down, facing up, facing down, right? Then this would be the bond facing up. Okay, this would be the bond facing down. All right, so now orange is going to end up on the bond facing up, and then 1, 2, 3. The red is going to be the bond facing up, and green would be the bond facing down. Cool. So this is where our substituents would end up. So what we effectively saw is that if you have a structure like this, right, orange, red, green, then if I'm drawing out a chair conformer, right, and if I number this as 1, 2, 3, 4, and this as 1, 2, 3, this is going to face up, right? This is orange, and then on 3, again, facing up is the red one, facing down is the green one, and this is now your chair conformer. Easy, right? So this is the logic, and let's talk more about that, or let's look at more examples of the same thing in the next video.